Hello, okay, welcome to the next video lesson. Okay, today I want to explain something. This is really quite important. Perhaps it's been said already, but I definitely have to explain this right now. Take a look at it. So you can see I've got my world router back just for a second. Okay, and you can see we've got some PC here at the college on the left side, trying to reach some Google server. Now, of course, this might not be Google. This could be just about any other server. Let's suppose it's got some big video that you have to download, and it's going to take quite a bit of time to download, like maybe 10-15 minutes. Okay, now here's a bit of a downside to the way how all of the physical networking works. Most of the time, these particular wires that we've been using, like this fast Ethernet connection and even fiber optic cable, these have limits, and the major limit that you're going to bump into is that when a particular network cable is busy doing something, it is busy for one person and one person only. So in other words, if you were to start a download from some internet site and it was going to take 10 minutes, it means that this wire would be completely tied up for 10 minutes and nobody else could do anything. Now, obviously, this is not the way how the internet works because, well, that would be absolutely silly because obviously there'd be lots of traffic going back and forth between Qatar and India. Okay, so unfortunately I've removed all of the other links at the moment. Okay, so the way how typically this is done is you have to share this particular connection. In fact, it's all the same. You share the connection based on time using something called time division multiplexing. And the way how it works is that one person uses the wire for a short amount of time, then another person uses the wire, then the next person uses the wire, then the next person uses the wire. And as long as the wire isn't used for a really long time by any one person, then you'd end up being able to get a lot of data. And this is actually okay because imagine this, if you wanted to download something, guess what? The entire movie would not make its way from this server over at this end down to this router. Instead, they use a very different mechanism called packetization. Okay, and that's going to be the secret that we're going to talk about today is this idea of something called packets. So what we do is we take a message and we break it into a bunch of little tiny pieces and we send the pieces one at a time over the wire. Okay, and what I've got is I've got a small simulation here set up between a bunch of computers and it looks like a router over at this end. I'll explain the trash can here in a second. Okay, so when you look at this switch, of course, you realize that, hey, look, there's one router plugged in, there's a bunch of computers. Well, is it possible for the computers to talk to each other? And yeah, of course it is, because we've been through a whole bunch of this stuff in Packet Tracer. But generally, this does not happen. For example, imagine this is a computer lab, and there are 6 students. Do the 6 students actually communicate back and forth directly from their computer to the other computer? Most of the time, probably not. Most of the time, the students in the room would actually be sending data off to some internet site, which is be on the other end of this router. So I'm not going to follow the packets any further. I'm just interested in the packets traveling from this particular computer to the other side. Okay, so the way this would work is that if this computer wanted to send out a packet, what would happen is this wire would become active for a short amount of time. Okay, how long? Well, it's going to depend on how much data is going to be sent. And of course, it would come into the switch, and then this wire would become active while the packet was transferred over to the next wire. So here, I'll give a small demonstration. You'll watch the packet will go into the switch and, of course, pop out the other side. Now, in reality, no, packets don't actually travel like little envelopes across the wire, but the wire is completely busy for the entire time that you're seeing this packet. So the first line is busy, it's busy, it's busy, and finally it's no longer busy, but of course then the output line happens to be busy. Okay, and no matter where you send the message, okay, it comes into one of the ports, it goes back out to the other end. Okay, so that's one packet at a time. Well, now what happens if we have a couple of packets? Well, as long as we leave enough space between the two, for example, here and here, you can see that, oh, whoops, I kind of showed something a little bit by accident. So let's get this one sent. Notice that I can use this wire while the second wire is in use. But as you've just discovered a second ago, it looks like there's going to be a problem when a packet arrives here. What about if this output line is already busy? So here, let me do this demonstration again to show you exactly this. So you see 2 packets reach at the same time. The first packet made it, but the second packet looks like it had to be thrown into the trash. Okay, and what this was this was simply because the wire was busy, and this is a bit of a downside to the way, or to this mechanism of packetization. If a packet reaches a device like a switch or a router, and that device is so busy it can't do anything, then it has no choice but to actually throw out the packet. In fact, if we were to do something like this, and try sending a whole bunch of things all at once, you'll see what happened is I ended up losing a whole bunch of packets, just because this wire happened to be busy at the time that the packets arrived. Okay, so what can we possibly do? Okay, well, there's a couple of options. The first option is, well, it's sort of too bad that it ends up throwing out the second packet right here. I mean, how come it couldn't just hang on to it for a little bit? All right, and what that is, that's called a buffer or a queue. And what most switches would end up doing is they would have a little bit of memory to be able to hang on to this packet for a short amount of time, and then of course send it out a little bit later. Now, what I say by a little bit of a short amount of time is, well, you can't hang on to the packets forever, okay, because packets have something called a time to live, and eventually they've got to be thrown out, because you don't want packets kind of sitting around and suddenly showing up at the wrong time sometime much later. Okay, so packets can only hang around for a short little while. And of course, the second thing is, can you imagine if I had, say, 100 computers all sending messages? Would there be enough room to have 100 messages inside this switch? Well, maybe there would be, but every message takes a little bit of extra memory. And of course, if you have too many messages you have to hang on to, it means that this device needs a whole bunch of extra memory. So that's one mechanism. And yeah, pretty much every reasonably decent switch in the world would at least hang on to a few things. It wouldn't just say, hey, it's busy, I'm throwing out the packet, like what I've done here. Okay, but it would hang on to at least a couple of them, at least for a short amount of time. Now, that's one way that I could get all of the packets through, but I've got another sort of interesting way as well. Notice what I've put down here. I've put a couple of input boxes where I've got something called the input speed and something called the output speed. Now, the output speed will control how long each of the packets are going to be on the output wire. And here, let me show you as an example. I'll make this one 20. Okay, and you can take a look at this. So this is going to send a packet here. It's going to be at its original 5 speed, whatever this means. And on the outside, whoop, okay, you can see it suddenly just disappeared. Okay, so it goes in kind of slow at 5 and it disappears very quickly at 20. Now, the reason why I might want to do that is because, well, take a look. If I send a couple of packets kind of close beside each other, I can actually get them both to make it through as long as the first one is completely finished. So as long as I leave enough room between the sends, again, not quite enough. Let me try one more time, maybe about here. Okay, so as long as the wire's completely finished by the time that second packet arrives, it's fine. Okay, well, what if I just go absolutely crazy and make this like, say, 50? Okay, well, let's take a look at one. So it comes in at this speed, and of course, well, it's going to disappear pretty quick. But now take a look. If I send a bunch of packets, you notice that I'm not losing quite as many as what I did before, because that outbound happens to be able to deal with that packet a whole lot faster. And again, a faster network cable, of course, doesn't mean that the packet actually travels at a faster speed, but it means that the time that the network line is in use is going to be considerably less. So in fact, even if I go up to something like 90, well, actually, let's go for 100. And let's take a look and see what happens. Okay, first of all, make sure we can even see it. Okay, it goes pretty quick. But you can see now it's actually dealing with all the packets. In fact, if I go through and I try sending all of these packets, hey, that's not bad. We ended up only losing one packet out of the entire thing. Okay, so that's another mechanism of being able to get rid of the packets, is simply have this outbound. Of course, the reason why I've picked this outbound to be fast rather than the inbound is because, well, this is where all of the traffic is going to go. Now, I'm going to come over here and I'm going to remind you of something that we kind of looked at. I did mention one time before, and now it's time to definitely point out why. Okay, back over to here in Packet Tracer. Do you remember we were using this 2960 switch a whole pile of times? And let me zoom in a little bit so you can see this once again. And of course, what we had before was we had a total of 24 ports here, and there was 2 extra ports down here. Okay, and if I go and I show you this configuration, you can see that there's a bunch of things called Fast Ethernet 01, 02, 03, all the way up to 24, and then there's two extra things called Gigabit Ethernet 01 and 02. Okay, so let me remind you, open Notepad, and let me remind you what these things are. Okay, the word Fast Ethernet. Okay, that is a network speed that happens to refer to 100 megabits per second. Okay, so that's simply a speed. So on this link, you can send over in 1 second. If you had 100 million bits, it would take exactly 1 second to go across. Okay, this is obviously much faster than what I'm talking about on this link. This is, I mean, this number 100 does not mean 100 megabits per second. It simply means that it moves 100 pixels every frame update. Okay, but it's the same idea. Okay, that's what Fast Ethernet means. The word gigabit Ethernet means 1 Gbps, which happens to be 1 equals 1,000 megabits per second. Okay, so it's 1,000 versus 100. Okay, so now that's the first thing. So obviously, when we covered that section, when we started wiring these together, and I made the suggestion that quite often we use these gigabit Ethernet links to hook up different switches or to different routers, this is exactly the reason why. It's to be able to handle this type of a situation. So you can see that one of these links, if this is gigabit, this is exactly 10 times the output of these, which means that, guess what? If I have 10 computers all sending at their maximum speed, the outbound link could still deal with this as long as the switch has at least a little tiny bit of packet buffering. So in other words, as long as you can hang on to at least a couple of things. So even if they all transmit, or 10 of them transmit at the same time, you could still get most of the packets through. Now, of course, if you're looking at this, you'll say, well, wait a minute, I have 24 inputs and I've only got one thing for an output. Well, it turns out that these two things right here, in fact, you can do these with all of them. But these two right here, once again, are sort of the typical ones that we end up using. It is actually possible to combine both of these together so that we can use, sorry, let me get this one over here. We could actually set up our output to use both gigabit per second Ethernet. So in other words, for output, we could actually configure to have 2,000 megabits per second, which means that now I can deal with 20 of these fast Ethernet connections and still not have any packet loss along the way. Okay, so I mean, this is something we're not going to cover in this course, but that's the reason why these things often exist. In fact, if you go and take a look next time you're on the college, if you want to take a look at something, in fact, I think what I'll do is I'll pop one open here because I think I've got one. The college is using a lot of these devices called 3560s. All right, and let's take a look. Okay, so the 3560s, okay, in this case, this 3560 happens to be using fast Ethernet along with 2 gigabit Ethernets, but the ones that we have at the college, a lot of these gigabit Ethernets, we actually have 4 of them, and everything ends up being gigabit on the input side as well. And these things might not only be just gigabit, but they might be what's known as 10 gigabit or using fiber optics. So that's the reason why we have a lot of these extra things, and usually I refer to these as uplinks because this is what they're used for. Okay, so this is often what we use is fast outbound to the uplink, and of course if you do need a router that's capable of dealing with the fast or this gigabit network connection as well. Okay, all right, so that's it for this particular part of the lesson. Check back. I think what I'll do is I'll stop this lesson here and I will make it in a separate video file. Okay, so check D2L for the next link.